Well, thank you very much, Roz, for the invitation to be here today. And it's really a great pleasure to have the opportunity to talk about some of these issues. How many people here think that you're getting an adequate amount of sleep? Wow, that's not too many. And how many are not? Wow. Okay, so we got some work to do here. I'm going to try to have you get sleep a little higher on your priority list. But I'm going to try to talk about how difficult it is to do so, particularly in our 24/7 culture. And I think one of the biggest issues that is perpetuating this sort of culture of sleep deficiency actually is our exposure to artificial light, particularly when the sun is not out. So I'm going to talk about that because I think that that is sort of where it all starts in terms of initiating this perpetual 24/7 activity. First of all, I want to acknowledge that the work that I'm going to be presenting is largely the work of our team of colleagues that I've had the privilege of working with over the past several decades, and by the support from many different federal agencies as well as individual organizations. Now, just to give you, I just show this picture because I was at the airport in Providence taking I think it was an 8 o'clock in the morning flight, and I was stunned when I looked in the lounge area before boarding that the entire Brown soccer team was asleep on the floor, and it just sort of was an indication of how sleep deficient we are in our society. So let me take a couple of minutes just to reflect on why in the world it is that we need to spend a third of our lives asleep. And I think that it's most likely the core function of sleep is related to the brain. I mean, sleep is ubiquitous among animal species, species that really can't afford to be completely offline, like some sea mammals, like the dolphin and the large whales. Sleep is so important that even though they can't be completely offline because they have to keep swimming and looking out for either predators or prey, they have a system where half the brain is asleep and the other half of the brain, has one eye open and is looking out, and then they switch off. So, and that just, to me, suggests that this probably isn't the biggest evolutionary mistake that was made, but that there is some core function to sleep. And as I'm going to discuss with you, there is evidence that sleep is critical for replacing brain cells. Brain cells and fat cells are the only real cells in the body that we don't replace. So, for example, our skin cells, our blood cells, most of our other cells in the body have a certain life, and then we make a new one. But we can't do that with brain cells. Our memories are stored in the architecture of those cells, which is a complex architecture even to begin with. And so we have to repair those cells, and the repair takes place when they are offline. Memory consolidation, as I'm going to discuss in a moment, is key and happens during deep slow-wave sleep. And then the integration of daily learning with prior experience seems to happen particularly in rapid eye movement sleep. So in one case, we store the information in file cabinets, and then we integrate that information with the other information that we have known. And sleep is not a unitary state. It actually, as many of you know, it has an architecture or a structure to it. And we don't exactly understand why that structure occurs in that sequence, but we know that that sequence of activities of deep slow-wave sleep at the beginning of the night and then alternating between rapid eye movement sleep and slow-wave sleep is critical for many of the functions of sleep. And it is also during sleep that we restore the energy that is critical for the brain to function effectively. So the brain only is 2 to 3% of the weight of our bodies, and it uses 20 to 25% of the energy that we consume. So every time one of those neuron fires, it uses a tremendous amount of energy. And so it disproportionately uses a lot of energy. And that's one of the reasons why it is so susceptible to damage. Because although we have a very clean burning furnace, it would probably get a LEED Energy Award, but nonetheless, it still produces toxic debris. And that toxic debris can be damaging to neurons. That toxic debris includes molecules like beta amyloid, which can be damaging to neurons, and if it builds up, it builds up in CNS conditions like Alzheimer's disease that are associated with brain damage. And so one of the functions of sleep is to clear out those toxins, which I'll explain to you in a moment. Now, one of the most exciting discoveries in this area was made actually here at MIT in the laboratory of Matt Wilson, right over in Building 46. And he was looking at place cells in the hippocampus and in the visual cortex. And he was having animals run through this figure-8 maze in this kind of direction. Now, it's very well known that animals, when they're running through a maze like this, within the hippocampus, you can tell where they are standing by which place cell, whether the particular cell in the hypothalamus in the hippocampus is firing, and that's why they're called place cells. So Matt wondered if he had the animals training on a maze like this in the running interval, he wondered what would happen during the time that they were sleeping in a post-running interval. And lo and behold, he found that when they were running, he could tell where they were in the maze by which place cell was firing. And that same sequence was repeating over and over again during sleep because they were replaying what they had experienced before, both in the visual cortex as well as in the hippocampus. And that really led to the discovery. He has since shown that that memory, the consolidation is disturbed if that replay is, if he interferes with that replay. And then in 2012 showed that he could actually reinforce the replay if he connected it, for example, with a tone and then repeated that tone during sleep, then they more often went through the replay. Now, I don't know if that means that if you listen to a tape of French during sleep, whether you're going to learn French. But anyway, there is a suggestion that the replay can be facilitated by yoked stimuli. And then the work of Giulio Tononi and his collaborators at the University of Wisconsin has shown, for example, that if you are practicing a psychomotor task, like with your right hand, like learning a sequence of music on a piano, then, and as you know, there is a specific section of the cerebral cortex that is linked, that controls the movement of your right hand, and a different part that controls the movement of your left hand, and your leg is controlled by a different part. Well, there is a phenomenon called local sleep. So the area of the brain that controls the part of your body that you have learned something new with actually goes into deeper slow-wave sleep the night after you have learned that information. And then you can do that task more reliably and more quickly the next day, even without any further practice. And Bob Stickgold, who I understand gave a lecture here last semester, was the first to discover, and published in this Nature paper, that if you learn a task on day 0, and then you sleep that night, and the next night and so on, then your performance on that task without any further practice gets better and better. And this is thought to be explained by the findings such as the one by Matt Wilson here and so on. If you don't sleep that first night, then even if you sleep the next night and the next night, so let's say you pull an all-nighter because you're really intensely involved in whatever, and you're applying what you've learned that day, then you never really get that improvement in consolidation of those memories. You might do okay on the exam on this day, but how many of you have ever, pulled an all-nighter to get ready for a test, and then a few weeks later you don't remember anything about what you studied? How many people have ever experienced that? Okay, great. Well, now you know why. So if you want to actually benefit from that information, not just to pass the test in the morning, but actually also to learn something, then you've got to sleep on the night after you acquire the information. Sleeping the next night or the next night just doesn't cut it. So when surgeons tell me, well, if we reduce the number of work hours, are we going to have to extend the training longer and have more years in our training to become a surgeon? And my response to them was, well, maybe the fact that you stay up all night every other night, maybe that's why it takes 7 years for you to learn how to become a surgeon. They don't like it when I say that. Now, there is, that controlled study has actually been done because since 1985 in New Zealand, they don't allow the physicians in training to work more than 16 consecutive hours. And they still seem to be able to train surgeons and whatnot. So, yeah, it can be done. Now, a really landmark discovery was made by Macon Nedergaard and published this last October, about a year ago. So what she discovered in the summer of 2013, and you wouldn't think any sort of major structure in the brain would be discovered in 2013, but she discovered the sewage system of the brain. Turns out not that many scientists looked into how the brain gets rid of its debris. We have lymphatic system in the rest of the body, but there's no lymphatic system in the brain. And nobody had wondered, gee, how do we get rid of all the garbage that goes into the lymphatic system in all the other parts of the body? And she discovered that along the blood vessels, surrounding the blood vessels, there was actually an area of where the interstitial fluid, the cerebrospinal fluid, gathered and was actually drained out from the glial cells in the brain, the support cells that support the neurons. And so, because this was similar to the lymphatic system but involved the glial support cells of the brain, she called it the glymphatic system. And then, that was big enough discovery. But then she decided to ask the question, gee, I wonder what happens when the animals sleep. Now, I don't know what possessed her to ask this question, but she discovered something that if you had asked me a year ago, what did I think happened during sleep, I never would have imagined that a structural change in the brain happened during sleep. But what she discovered and published this past year was that this glymphatic system, which is illustrated here in this micrograph, that the flow rate through that glymphatic system goes up somewhere between 10 and 20-fold, because actually the size, it would be as if in Manhattan, there's always the garbage, in all the streets during the daytime when you're walking around. Well, it would be as if the alleys got bigger and the sewers got bigger, and because the building shrunk, so that during the night they could get rid of all of that garbage more efficiently. And so there's actually a 60% increase in the interstitial space with much more rapid flow, 10 or 20 times faster flow. So if she puts some gunk in the brain to see how fast it perfuses during wakefulness, when all the cells are expanded and the interstitial space is narrowed, it only progresses this far during a given interval of time. Whereas during that same interval of time during sleep, because the space is so much larger because the cells shrink, it flows through much faster and the flow rate is much better. And we get rid of the beta amyloid and other toxins that accumulate during wakefulness as a byproduct of the combustion that's going on in the brain. So if you stay awake continuously and pull an all-nighter, not only are you not consolidating those memories, but you're also building up toxins that are damaging the neurons in your brain, which may be why people get headaches or whatever else is happening when they stay awake. We don't know, that's total speculation, but in any case, there is this does suggest that we are damaging or letting debris that damages neurons build up when we don't get the sleep that we need. Now, because of that tremendous energy usage that occurs during wakefulness, and because we haven't restored that energy by sleeping, if you stay awake for 24 hours, and how many have pulled an all-nighter here? Well, let's do it differently. Is there anyone who has never pulled an all-nighter? Okay, great. Congratulations. So if you look at energy utilization after 24 hours of wakefulness, you see that, and this is the blue area represents decreased or degraded glucose utilization. And you see that the prefrontal cortex, that is the area of the brain that's critical for judgment, for example, has and control has much less glucose utilization in the tissue. The thalamus that relays sensory information to the motor cortex is impaired. The inferior parietal cortex that integrates that sensory information from the various sensory organs is impaired, as well as the visual cortex. But it's really the prefrontal cortex that I think it's the impairment in that region that is associated with certain specific phenomena that happen when you are sleep deprived. One of which is a phenomenon called automatic behavior. So we have a situation in which it appears that one part of the brain can fall asleep while the other part of the brain is still awake. Remember I talked about local sleep and how you can get deeper sleep? Well, here it's a slightly different concept where the local sleep can happen involuntarily. How many of you have ever been driving along on the expressway and you can't remember how you got from point A to point B? Has that ever happened? Okay, so the car somehow was driving itself, and you weren't fully engaged. And people can do some crazy things in that situation. One woman came to Bill Dement to see him because she had loaded all of the dishes into the dryer, and then when she pushed the start button, it was only then, when she heard all the dishes being smashed against each other, that she realized that she had been in this phenomenon, which is called automatic behavior. Sometimes you may be so sleep deprived that when you're writing something, you realize that you've written nonsense or that it's not related. How many of you have ever experienced that you're so tired that, yeah, okay. So, but it most commonly happens when you're driving a car, and it's extremely hazardous. One of the first instances that I was involved in, a tragic instance, was when an individual in Massachusetts out in Pittsfield was driving, and it was a 2-lane highway, sort of 45, 50 miles an hour in each direction, as happens in rural areas. And he was going in one lane, and then the witnesses said he crossed over and began heading toward the car of a woman who was coming in the other direction. Now, she was obviously alarmed by this, and witnesses said, went into the other lane. Then he tracked her into that lane. Then she went back into her lane, and he kept tracking her. And that seems to be something that when the brain, and one thing that if you remember nothing from what I'm talking about today, if your car is disabled and you're sitting at the side of the road and you have the flashers on, do not sit in the car waiting for someone to arrive, because I can't tell you the number of people who are blown off of the highways by truckers or whomever who see those flashing lights, and like a moth to light, they will go toward them when part of the brain is asleep. So he tracked this individual back and forth between the lines, and he said he sort of came to a fraction of a second, and he could see her terrified face through his windshield the instant before he killed her. So it is extremely dangerous driving when you're drowsy. And he was probably the first person in the United States who was convicted of vehicular homicide for, although this has now happened in many, many states, in various incidents that have happened since then. That was in 1994. So the other thing that happens when we're sleep deprived is that we become much more emotionally volatile. And Matt Walker, working with Sunshik Yu at the Brigham Women's Hospital, did an interesting imaging study in which they looked at the emotional center of the brain, the amygdala. And here you see the individuals who are rested, and in response to disturbing images that they were shown in the scanner, you see they have a very modest response in the emotional center of the brain. And those same individuals, when they were sleep deprived and shown the same type of disturbing images, you see the response is tremendously greater. And you can see that it's almost a tenfold increase in the number of voxels that are activated and the extent of amygdala activation. And what makes matters worse is because the prefrontal cortex, that judgment area of the brain, because it is going offline when we're stayed up all night, there is a disconnect between the amygdala and the prefrontal cortex that can be seen in this imaging. That shows that the connectivity between the judgment area of the brain and the emotional area of the brain has been degraded. Doc Rivers, who was the coach for a number of years of the Celtics, likes to tell the story that they had a couple of back-to-back games. One was in Portland against the Trailblazers, and they were doing very well, and they had beat them. But I had told him that when they had these back-to-back games, the NBA requires them to fly all night. And they were going to against the Phoenix Suns in Arizona, and I had said, this is going to be a problem because if you're going to take a flight right after the game, but they didn't want to take a flight the next day because they get fined $1 million if they miss the game, if they're not there when the TV cameras are on. And so they flew that night. But then the next day, when he was screaming at the ref and thrown out of the game, and got a technical, as he was sitting in the locker room, he remembered what I had said about the vulnerability in terms of your ability to control your emotional responses to, for example, in a situation like that, he probably thought the ref had made a call that was inappropriate. That happens all the time. But in this situation, that's when you get thrown out of the game if you can't, if you've been up all night and have a reduced ability to control your emotions. Now, one of the other things that happens that's related to the impairment in performance associated with driving a car is that, it's one thing if you're just studying and then you're going to walk to an exam the next day. But if you're up all night, if you're up all day and then you're up all night, as was, for example, the driver who ran into Tracy Morgan and resulted in those injuries recently in New Jersey. And this is why they have a law in New Jersey, which he was charged under for, if you've been awake for 24 hours, it's considered to be equivalent in terms of your impairment to being legally drunk, because the studies indicate that 24 hours of wakefulness indicates an impairment, induces an impairment in your neurobehavioral performance that's equivalent to a blood alcohol concentration of 0.1%. So your average reaction time, which is indicated in the open circles here, goes from about 1/4 of a second to over a second. So that means it's going to take 3 to 4 times longer for you to put your foot on the brakes, even if you remain awake. And 1 out of 10 of your reaction times is going to go to 5 to 6 seconds, which is enough time for you to drift off of the road and slam into an embankment if you're approaching a bridge or whatever, all of which has happened on multiple occasions. But even if you remain awake, it's going to take you substantially longer to react. So yes, maybe the other driver did do something stupid, but normally you would be able to avoid a collision. Maybe the kid did run out in front of you when you were driving along the street chasing a ball. But normally you would be able to stop in time before killing that child. So here, the danger that's associated with trying to do something like driving when you've got an insufficient amount of sleep is that it really does degrade your brain's ability to respond. But it's not just the brain that is affected by. So remember when I began by saying the core function of sleep probably has to do with these key functions in the brain, and the fact that we need to repair the brain, replace the energy supplies, and get rid of these toxins. That's probably the core function. But as in most of evolutionary biology, when you have some key function like that, then many other things get tacked onto it. And it appears that many bodily functions are critically maintained by getting the sleep that we need at night. And so if we don't get enough sleep, there are many adverse physiological effects that are even beyond those that happen in terms of the brain. So teenagers who get an inadequate amount of sleep have higher blood pressure. Adults, if they are sleeping an inadequate amount, have a 300% increased risk of calcification of the coronary arteries, for example. The immune system is adversely affected so that, it's the flu season now. So if you go out and get a flu shot, if you've only been sleeping 4 to 5 hours a night in the week before you get that flu shot, you'll only have half of the antibody response than if you had an adequate amount of sleep in the week before you got the shot. I'm not talking about after you get the shot. I'm talking about before you get the shot. And sleep deficiency also adversely affects metabolism. I don't have time to go into that today, but within a couple of weeks in our laboratory, we can put many people in a pre-diabetic state just by restricting the amount of sleep and also disrupting your circadian rhythms during that time. And the epidemic of sleep deficiency, which the Institute of Medicine has estimated affects about 50 to 70 million Americans who are chronically sleep deficient, is thought to have played an important role in hypertension, diabetes, obesity, depression, heart attack, and stroke. Now, to put this in perspective, if you don't feed an animal like a rat, in 2 weeks, that animal will die. If you deprive that animal of sleep but give it an adequate amount of food, in 3 weeks, that animal will die. And even if you allow the animal to sleep, but you selectively deprive the animal of rapid eye movement sleep, it will also die in several weeks. So it appears that we need not just to sleep, but we need certain types of sleep in order to survive. And what happens to the rats is that they begin to, their metabolism is affected. They eat more food, but they lose weight. They can't defend their body temperature, which then goes down if they're exposed to a cold challenge, and they deteriorate and ultimately expire. And interestingly enough, if you allow them to sleep, if they're on the edge of death, and you allow them to sleep, they recover within a day or two, back to where they were. Now, as I mentioned at the outset, sleep has structure. And so I'm showing you, just for fun, some sleep recordings that we did in space, because it was kind of cool at NASA Control to see these things as they were beamed down from space while the astronauts were sleeping in their sleep chambers. They hooked each other up with these EEG nets, and then we could see as they were falling asleep. This is stage 1 sleep. This is 30 seconds of a recording, and you can see the eyes rolling around in their sockets. I'm hoping somebody will illustrate that today, and then I'll point that out to everyone so that you can see the eyes rolling around in their sockets. I've been looking, but I haven't seen anyone do that. But if it happens, we'll be sure to do a demo. I doubt that anybody will get to stage 2 sleep. When that happened, Bill Dement used to have a squirt gun in his class, and he would squirt them if they got to that stage. He warned everybody in advance, but I don't have my squirt gun with me. But anyway, so here, this is when we can actually, at the surface of the scalp, begin to detect the synchronous firing of cells in the brain, and this is a K complex, and then there are sleep spindles. So and then as you progress during the night, within the first hour, you go into this deep slow wave sleep, which is these days called stage 3 sleep, and you see the synchronous firing of these cells. And then another stage of sleep, but it's really a completely different state of consciousness, as different from slow wave sleep as wakefulness is from sleep. And that is this rapid eye movement sleep that I was telling you about. And you can see just the clue to the fact that this is so different is that the brain waves, there's no evidence that the individuals are asleep, or very little evidence that they're asleep. It looks almost like wakefulness. In fact, the French tend to call this paradoxical sleep, because it's paradoxical because the brain waves look like you're awake, you're paralyzed, and your eyes are darting back and forth in their sockets. And in fact, when the EEG was first discovered and being recorded by scientists here in Boston and elsewhere, they thought, well, aren't we clever? Because we can see that the people, they look like they're asleep, but they're actually awake. Well, they were wrong. They thought they were awake based on their EEG patterns, but then it was Azarinsky and Kleitman and Bill Dement out at the University of Chicago who said, hold on, they look like they're awake in terms of their brainwave recordings, but they actually are asleep. In fact, it's as difficult, and in some cases more difficult, to arouse them than it is from deep slow wave sleep. And when they looked carefully at these sleeping people who looked like they were awake from the EEG point of view, they saw that their eyes were darting around. And we actually have an area of the brain that is paralyzing our muscles, so that we can't, at the level of the spinal cord, so that we can't actually act out our vivid dreams that we are having at this time. And they discovered that this, if they did wake people up, that they were having vivid dreams. You can have dreams in other stages of sleep, but the highest percentage of dream reports, and the most vivid ones with action, happen during rapid eye movement sleep. Now, so what happens? So I told you that sleep has structure, and we have most of the deep slow wave sleep, and this is slow wave activity, in the beginning of the night. And so we can plot this in different ways. These are the different sleep stages. This is the spectral analysis of the EEG showing the power density of slow wave activity. And now you see that we begin to have rapid eye movement sleep, one bout of rapid eye movement sleep, then another major bout of rapid eye movement sleep. And these bouts happen about somewhere between every hour and a half and every 2 hours for the rest of the night. But you notice that most of the rapid eye movement sleep, which I told you was critical for life, and also critical for integrating our memories with what we had known before, most of that, you notice, happens in the latter half of the night. So what do you think? How many of you have ever just sort of, you had to go to the airport, catch a 6 a.m. flight, whatever, and you just set that alarm and truncate 3 or 4 hours from your sleep? How many of you have ever done that? Okay, so what do you think happens? Do you think you just get half of your normal amount of sleep? No, you just wipe out this part, because the brain doesn't have any warning that that alarm clock is going to go off. So that alarm clock specifically targets rapid eye movement sleep. So when you get up without, a century ago, 95% of kids in school woke up spontaneously without an alarm clock. 95%. These are studies done by Louis Terman, who was the one who developed the IQ test and was chairman of psychology for 20 years at Stanford. And he said, we must never start schools before 9 o'clock in the morning, grade school and high school, because if we do, we're going to be damaging the timing of sleep. And he was very prescient. Of course, we have since moved all the schools to the 7:30 start time. Now, nobody listens to academics, you see. So if we really want to look at sleep deprivation, the profession that has sort of taken this to an extreme is the medical profession during the training of their resident physicians. So it's interesting to me to look at the history of this, which I got some insight into from an article that was published in the New England Journal in 2005. And the title of this article was The Accidental Addict. And why did they call this? So we owe the residency training program structure in the United States to William Halsted, who founded the surgical training program at Johns Hopkins about 125 years ago. And he was renowned for, he required the doctors to live at the hospital, and they often worked these marathon shifts while they were living there. And he was renowned himself for being able to stay awake for extended durations of time. But it was only revealed 115 years later that he was actually a cocaine addict. In fact, and that's probably how he was able to sustain those tremendous durations of wakefulness. He had, the reason why he was called an accidental addict is because he became addicted to cocaine testing it as a surgical anesthetic. And so it was, quote unquote, not his fault. He was treated at the Butler Hospital just around the corner from us in Rhode Island, where he was an inpatient for 1.5 years trying to get him off of his cocaine addiction. And they used morphine to try to get him off of his cocaine addiction. And guess what? He was discharged 1.5 years later as a morphine addict and a cocaine addict. So he had what the Air Force would call his go pills and his no-go pills. And that also explained why he had his shirts laundered in Paris, because when they came back, everybody thought that was a peculiar thing, but they came back with the cocaine packets within them. And I don't know if this happens today, but he was hired as a full professor at Johns Hopkins directly out of his 1.5 years in treatment at the Butler Hospital. So they took him right from rehab and put him in charge of the residency training program. And that's how we have this system of training physicians here in the United States 125 years later. And pardon me?
How did he function?
I don't know. I wasn't there. But he is very beloved there. I can tell you that when I presented this at Johns Hopkins, it was not well received. Anyway, when we have tested resident physicians working the 30-hour shifts as compared to shifts that did not exceed 16 consecutive hours, we found that those extended duration shifts were associated with twice the attentional failures at night, 36% more serious medical errors, 460% more serious diagnostic mistakes of patients in the intensive care unit. And then driving home, the residents working the extended duration shifts had 168% more car crashes driving home from those shifts, many more near-miss crashes. They stabbed themselves, they had a 73% increased risk of stabbing themselves with a needle or scalpel. And even, it's not just trainees, but even attending physicians had 170% increased risk of complications in patients undergoing elective surgery. For example, on a Tuesday morning, if that surgeon was on call all night and had less than a 6-hour opportunity for sleep the night before. So if you are having an elective procedure, you might want to ask, have you been up all night the previous night? So, but that's sort of an extreme case. I don't really want to dwell on that, although I did spend about 1.5 decades doing those studies. But what I want to talk about is really the much more chronic sleep deficiency that is pervasive in our society and the impact of that. Because I presume that most people are not working 30-hour shifts every other day, but most of us are nonetheless sleeping less than in yesteryear. I talked about the landmark studies that Lewis Terman did on the West Coast, where he studied 2,500 school children. This study, this undergraduate thesis project at the University of South Australia, a student gathered together meticulously data from 750,000 students that had been collected over the last century in various studies that were done in a meta-analysis that she did. And she found that the number of hours that children of all ages, 5 to 8-year-olds, 9 to 12-year-olds, 16 to 18-year-olds, and so on, that the number of minutes that they slept on average in studies throughout the world has been decreasing steadily across the last century. And in fact, in the United States and Europe, the median nightly sleep duration has declined an average of 1.15 minutes per year for the last century, meaning that today, students of all these different ages are sleeping about 2 hours less per night than they did a century ago. So now, if we, knowing what we understand about the importance of sleep for learning, for metabolism, for health, we could certainly not do, we would never get permission from an IRB to take children for years and have them sleep 2 hours less per night for an experiment, because it would be considered unethical. And yet we're doing that to our children. And it's having manifold consequences. We know that just in terms of brain consequences, I've already talked to you about the effects on learning. Children, instead of becoming obviously sleepy when they are not getting a sufficient amount of sleep, as most mothers will soon, as will become evident to most mothers, and we have a mother here, and I'm sure when your child is about 2 years old, you'll find that if the child doesn't get an adequate amount of sleep, they become incredibly cranky and difficult to behaviorally control. And mothers will readily say at that point, well, Johnny or Susie has not gotten enough sleep, and that's why she's a nightmare when we're trying to have a family gathering or whatever. And so one of the characteristics of children when they don't get enough sleep is hyperactivity and reduced attention span. They also become increasingly distractible, as do adults, and a reduced ability to focus attention. And increased irritability, mood swings, and it also increases the risk of depression and suicidal ideation. So children whose, high school children whose parents don't set a 10 p.m. bedtime have an increased risk of depression and suicidal ideation. It also is associated with impaired balance and control. So what do you think that these cognitive and emotional what do you think that these changes that are associated with sleep deficiency, if a child is experiencing this sleep deficiency night after night after night, what do you think that sets them up as a potential misdiagnosis for? ADHD, right. Because there's no hard guideline. If the child is having difficulty with any of these symptoms and the teacher says, this kid is a nightmare in class. By the way, I was stunned when I brought my now 19-year-old daughter when she was 5, and I first brought her to kindergarten. And we all sat in the classroom as nervous parents with our first child going to school, and we're in a kindergarten classroom. So I'm sitting in the little tiny, kindergarten child's seat, which was somewhat uncomfortable, at this little tiny desk, listening to the teacher, and she said something that really shocked me, because she didn't know who we were and what we did for a living. And she said the most important thing that you can do for your child to get them ready for school is to make sure that they get an adequate amount of sleep at night. So I thought, well, this is music to my ears. And then she said, I can tell, but she was not just saying this she was saying this because of the impact that it had on her. She said, I can tell within the first 10 minutes of your child arriving in my classroom if you have kept them up at a shopping mall or whatever the previous night. And she said, I will call you up and tell you to pick up your child because I'm not going to deal with it. And I thought, whoa, this is one tough kindergarten teacher. But she had been through this enough that she was not going to do that, and she had already in her decades of experience, recognized that this was a critical issue. But many teachers don't see that connection. And instead, if that child is recurrently coming with that, they'll simply send them off to the school nurse, who will send them to the doctor. And then what do we give them? What do we give them to treat them? They have wonderful names: Concerta, Adderall, Ritalin. Do you know what they are? Okay, we call it stimulants. What? Come on, let's call a spade a spade. Does anybody know what? Amphetamines. Now, when I was growing up, if pushers had given children amphetamines, they would be in jail. In fact, some of the people who did sell amphetamines to children in the 1970s are still in jail because the sentences were so long. And yet now, by marketing this, in this very clever way, and I'm not saying there aren't children with ADHD, but the number of misdiagnosed children, and we know that they're misdiagnosed because some of them have obstructive sleep apnea. They snore when they sleep, and they can't get the sleep that they need. And they may be taking amphetamines for years, and there have been many, many reports of this. And then somebody realizes that they have sleep apnea. They take their tonsils out, which is usually curative of sleep apnea if they're not obese, and in children. And suddenly, they don't have to take amphetamines anymore. So we know that sleep deficiency can mimic the symptoms of ADHD and can be treated with amphetamines, and is often treated with amphetamines. But usually when I said this, psychiatrists would go insane and say that I don't know what I'm talking about. So I was very pleased last year, about a year and a half ago, when a card-carrying psychiatrist wrote an op-ed piece for the New York Times and said, it seems odd that 19% of high school boys in the United States are diagnosed with ADHD. And he even got some of the folks, he talked to some of the folks who had originally pioneered the recognition of ADHD, who said, now this is getting totally out of control because it can't possibly be that 1 out of 5 boys has a condition that was basically unheard of 50 years ago in children of the same age. And the problem is this is now bled over to college. So now amphetamines are considered, and here at MIT there's been some wonderful writing by students here who talk about the routine use of amphetamines as study drugs. How many have heard about this here at MIT? Yeah. And 25% of college students nationwide now use amphetamines routinely as study drugs because of the sleep deficiency that they're experiencing. So the average, and one of the reasons why parents don't recognize that their children are not getting enough sleep, first of all, they don't necessarily realize that they need 9 to 10 hours of sleep, even through high school. Because the parents themselves are only on average sleeping 6 to 7 hours a night. And the percentage of Americans sleeping less than 6 hours a night, which was less than 3% of the population when I was growing up, is now 10 times as great, to 30 to 40% of employed Americans. So the parents might be getting 5 or 6 hours of sleep. And so if their kid is getting 7 hours of sleep, they're like, whoa, this kid is sleeping way too much. And they don't realize that the developing brain needs more time to sleep. Even though 70% of Americans report, just like you all did at the beginning of this discussion, that they're not getting enough sleep. And as if we didn't need any more evidence, I still find this statistic shocking every time I see it. And I was just at a National Transportation Safety Board meeting last week, the first time that they've ever had a forum on drowsy driving. But to my astonishment, 1.75 million Americans fall asleep at the wheel every week. It's 280,000 people a day fall asleep at the wheel. Isn't that just stunning? 8 million Americans every week are so drowsy that they are struggling to stay awake while they are driving. So they know that they've not gotten enough sleep. They know that they're struggling to keep their eyes open, and yet they're driving 60 miles an hour on the highway. If you are struggling to stay awake, stop driving. It is incredibly dangerous. It's much more dangerous than driving drunk, because if you actually lose the struggle, first of all, your reaction time is going to be much longer, as I discussed, and it's going to take you longer to react to situations, but even if you stay awake. But if you go to sleep, you are essentially in a missile that is not being controlled by anyone. And the brain, we think that we are going to control whether or not we fall asleep. But the brain can seize control and make the transition from wakefulness to sleep involuntarily. And that's why we have, for all these reasons, 1.2 million drowsy driving crashes annually. So every half minute during this discussion, there's been a drowsy driving crash. There are 500,000 injuries associated with drowsy driving every year. 55,000 of them are debilitating, and about 7,500 fatalities every year. So there'll be at least one or two during this discussion. Now, you may be thinking, I'm young, so I can do it. I have the right stuff. I'm tough enough. The crazy thing about the way this system works is that it's easier for me to stay awake all night than it is for the students here, because the peak time of vulnerability is when you are young. It is when the brain's ventrolateral preoptic area, which is the sleep switch, has all of the cells, because we lose cells in that area of the brain more than other areas of the brain as we age. So by the time somebody is maybe 70 years old, they're going to only have half the number of cells in that region that has to fire when we make the transition from wakefulness to sleep. And so when we keep people up in the laboratory, and it's funny thing is that when we first started doing these studies, the entire investigational review board of our hospital came to the laboratory, because they said, oh my God, you're going to be keeping grandma and grandpa awake all night? You're torturing them. You can't do that to older people. But we were comparing for the National Institute on Aging younger versus older people when they stayed awake all night. And lo and behold, when we look at the reaction time, you know, young people pride themselves on being able to play video games and react quickly and so on. Well, here's the young directly. I haven't normalized anything here. The young directly compared to the older people. So here you see the reaction time. Remember I told you a quarter of a second. And now we keep them up all night. And the old fogies are doing pretty well here. They only go up to about a half a second. Whereas the young ones, their average reaction time is going up to a second and a half. They're just falling apart, because the sleep system is working better. There's a reason why these older people use 90% of the hypnotics, sleeping pills that are sold in the United States, because they're having trouble making the transition from wakefulness to sleep. It gets harder as we get older. It's not hard at all when you're young, and the brain will involuntarily seize control. So because you are so fit from the point of view of how your sleep system works, you are actually more vulnerable when you do violence to the sleep system by staying awake all night. And that's why younger people are at greater risk for drowsy driving crashes. And you can see the drowsy driving crashes peak in your 20s, not in your 70s. So the big question is, why are we sleeping less? Can I get a time check? Because I have no idea. There's no clocks. And this feels like my laboratory. No clocks, radios, information sources as to the time of day.
We have about 20 more minutes before we have to
Okay.
begin.
Okay, great. So why are we sleeping less? It's this nocturnal exposure to artificial light, I think, that I'm going to try to convince you of contributes to the epidemic of sleep deficiency. I'm going to run through this quickly. As lighting prices have declined since the 1300s dramatically, this is a log scale, our per capita use of lighting has dramatically increased. Going up tenfold just in the last 50 years in terms of our per capita usage. If we go to areas, as I did here, to a remote area of Brazil that is not electrified, and I asked this woman with the 7 children, including very young children, how they all slept in one room on a dirt floor, and what did they do to light the kerosene lantern, how did they function when one kid after another was waking up during the night? She didn't even understand what I was saying. And finally, Professor Lusada, after translating for the 3rd time, she suddenly recognized what we were saying and said, no one gets up during, the children, they say we go to bed at dusk and get up at dawn. And it was such a foreign notion that the kids would be awakening during the night that she didn't even understand what I was talking about. So we have some idea that things have changed with the introduction of artificial lighting. To understand why this is important, we have to step back for a moment and understand that the circadian pacemaker, the internal clock in the brain, controls the timing of when we sleep and wake. And so here we can look at many outputs of this hypothalamic pacemaker located in the anterior region of the hypothalamus on either side of the third ventricle that drives circadian rhythms in the release of melatonin, in eye movements. These are the slow eye movements that I was talking about. So the peak time that we're likely to experience this involuntary transition to sleep is very near the red vertical line here, which is our habitual wake time. And the time that we're least likely to experience it is right near our habitual bedtime, because the circadian pacemaker sends out the strongest drive for wakefulness just before you go to bed at night. Kind of crazy. Just before you go to bed at night, and the strongest drive for sleep just before you get up in the morning. So there's this tremendous surge in waking just before what your brain would expect to be dusk. And this occurs in most day-active species, just before dusk. Now, can anybody think of why that might be important to have a surge of energy right before it gets dark during evolution?
Maybe not the safest time.
Pardon?
Maybe it's not the safest time.
Yes, you got to get your act together before the sun sets, because once the sun sets, if you're not in your cave or whatever's happening, if you're not in a protected place, then you're going to be in trouble because you can't see anything and other animals can. So most species have this surge of activity right before they have to do their nesting or whatever has to happen. And we have this surge. How many of you noticed that in the period before you ordinarily go to bed at night, even if you're exhausted and you can't function in the morning when you get up because you're not sleeping enough, but suddenly in the evening, you're like full of energy. How many of you have ever noticed that? Okay, the entire group. Okay, good. And it's kind of strange because you recognized in the morning, and unfortunately, it's happening at the time that you have to make the decision as to whether you're going to go to bed, and you're not tired. You're like, wow, oh my God, this morning I felt like dirt when I got up, but now I'm fine. And so that is because of this surge in energy that happens, with it taking the longest for us to fall asleep at any time of day. If we put people to bed at all different circadian phases, the peak drive for wakefulness is just before bedtime, just before our habitual bedtime, which is indicated by the vertical dashed lines here. And it is the release of this sleep-promoting hormone melatonin that quiets the waking drive, the output of the waking drive from our suprachiasmatic nucleus in the hypothalamus, and allows us to maintain consolidated sleep where we have very few interruptions, which are indicated by these black bars, during the sleep episode. And so this is what we could call a second wind that happens in the late evening. And it helps to consolidate our wakefulness. We're not like most mammals. We don't take little rat naps and cat naps throughout the day. We have this marathon of 16 hours of waking, even though we don't consider that enough. But relative to other mammals, it is tremendously long. Now, the average period of the output of this pacemaker in the brain is longer than 24 hours. So we have this pathway from the output of the circadian pacemaker to the pineal gland that releases the hormone melatonin. And if we're in continuous darkness, this will drift to a later and later time each day. And we have studied many people in the laboratory, and most people drift later and later each day with the output of this pacemaker. But a few have a shorter than 24-hour period and actually drift earlier. This is the time of day here. Men tend to have a slightly longer period of the circadian system than women. It's only a difference of about 1/10 of an hour, but it means that 3 times more women have a shorter period, shorter than 24-hour period, than do men. And this is important because individuals that have a shorter than 24-hour period are continuously going to be drifting to an earlier hour and are going to need to have their circadian pacemaker reset by dusk rather than by dawn. So it's going to be the evening light that synchronizes them to a later hour, as opposed to the morning light. And when you start getting a period that's even longer than that, it's harder to keep in sync with the 24-hour day. So if we look at this, if this is your regular bedtime, and this is the period of the circadian system, you can see that individuals with a shorter than 24-hour period may be releasing the sleep-promoting hormone melatonin 5 hours or more before their regular bedtime. So that means, like, during dinner. So this person is not going to be the life of the party because, their brain is already releasing this sleep-promoting hormone many hours before their usual bedtime. The flip side of this, and we think that this may contribute to the fact that more women suffer from insomnia, is that during the middle of the night, now it's 3 or 4 o'clock in the morning, that hormone is gone because it's only secreted for about 8 to 10 hours. And so once that's gone, it's time to wake up, even if other people have kept that woman awake in the evening, so could not go to bed at dusk, like the woman living in Brazil, has got to stay up, be with everybody, be with the family, do whatever. And now, when going to bed at, let's say, midnight, has only got 3 or 4 hours left in their biological night before it's morning for that individual. Whereas an individual with a longer period is not even going to be tired until just before or even after midnight. And since that controls the ability to sleep, it's really very difficult. How many of you have noticed that if you try to go to bed a few hours before you usually do, it's really tough because you're trying to go to bed in that wake maintenance zone? And so people say, well, I'm used to going to bed at 2 o'clock in the morning. I've got an early exam, a plane, whatever, fill in the blank there. And so I'm going to try to go to bed earlier. Can't fall asleep. So they go to the doctor and they say, I can't fall. Even if I try to go to bed at 10 o'clock, I can't fall asleep. Give me something. And so they go to the health services, and the health services gives them a sleeping pill. And so now they have the amphetamines to stay awake during the daytime, and they have a sleeping pill at night, and you're getting very close to Professor Halstead with his cocaine and morphine combination. So women, on average, their circadian clock is set somewhere between an hour to an hour and a half earlier, all other things being equal, even if you're maintaining the same bedtime and wake time as men that were matched for their bedtimes and wake times here of the same age, same schedule, and so on. The women were still, their internal clock was set to an earlier hour. So now the daily cycle of light and darkness synchronizes this hypothalamic pacemaker to the 24-hour day. So under normal circumstances, the light information is coming through here, going down this crazy pathway up to the pineal gland, and then it remains in sync with the 24-hour day. And that's how we entrain our internal clock that has a non-24-hour period to the 24-hour day. And so that's great, and we normally, but the problem is if we're exposed to light during the night when we're normally releasing this hormone, it drops down immediately, and we suppress the release of this hormone because we're telling the brain it's actually daytime. So the brain begins the process of shifting and accommodating to that as daytime rather than nighttime. And then we don't feed back this hormone to turn off the output of the SCN, so it continues to send the waking signal if we suppress the release of the hormone. So so normally, in somebody who goes to bed at midnight and wakes up at 8 o'clock in the morning, light in the evening resets the circadian system to a later hour. Light in the morning resets it to an earlier hour. And this is why our second wind is placed here late in the day at around 10, 11 o'clock at night for somebody going to bed at midnight. Ordinary room light has about 50% of the resetting effect of the brightest light on a clear day outside. So, and this is, not linear. So even though this is only 1% of the light intensity, it has 50% of the resetting response. So our artificial light is actually very, very powerful. And just as the ear has two functions, one is hearing and the other is balance, the eye has two functions, one is vision and the other is circadian photoreception that mediates this resetting. And we can even show in some blind people that have this system preserved, even if they've lost their rods and cones and can't see anything, we can suppress melatonin and reset their circadian rhythms with light that they can't see. I'm going to have to skip the neurobiology of how this works, but take my word for it that there is a completely separate system in the eye, and we have intrinsically photosensitive ganglion cells that mediate that circadian photoreception. And those intrinsically photosensitive ganglion cells are more sensitive to short wavelength light. probably because they are vestigial or evolved from marine organisms, which were primarily exposed to blue-enriched light. And so blue-enriched light has twice the resetting effect and a much greater ability to suppress melatonin than does light at the peak of our photopic sensitivity function of the cones, which is at about 555 nanometers. So light after dark suppresses this sleep-promoting hormone, increases alertness, shifts our circadian rhythms later, and interferes with sleep. And yet we are suffused in light by our exposure to artificial light, which decreases the duration of the secretion of this nocturnal hormone by about an hour and a half, and shifts us to a later hour. So remember this daily sensitivity rhythm to light. If we imagine what that might have been 200 years ago, where darkness would have been from 6 p.m. to 6 a.m. instead of starting at midnight, then our second wind would have been in the middle of the afternoon when everyone is running to get a Starbucks or some other caffeinated beverage. And we wouldn't be tired at that time of day. But it's the exposure to artificial light after dusk that has shifted us all by 4, 5, 6 time zones westward, as if we were in Hawaii instead of in Boston. So our brains have been shifted to Hawaii. And we don't even think of midnight. That's sort of for many people. How many people, when they see midnight, they think maybe I should check my email? How many people, or texts or whatever? Yeah, exactly. We don't even realize that the word is midnight because it's actually in the middle of the solar night. It's not the beginning of the night. And so we have moved this second wind to be so late in the evening, and actually, so if we think of this, where this wake maintenance zone is, it has moved from the afternoon to, let's say, the evening in someone who is on a regular schedule and adjusted to this. But in many people who have a delayed phase of their rhythm, it may be moved such that they don't even hit the time that they can fall asleep until 3, 4, or 5 o'clock in the morning. And so this big squeeze has been created with this early wake time required for school, work. The biggest growing sector of the workforce in our society, in our service-oriented society, are people whose jobs begin between 3:30 and 6:30 in the morning. So we have this tremendous need to start things so that somebody can be giving you your Starbucks at 6 o'clock in the morning at a very early hour. And yet we have this circadian surge in wake propensity that is occurring in the evening. And sleep is getting squeezed between these two vices. And it's only going to get worse unless we do something clever. And that's because whereas incandescent lamps had most of their energy in the longer wavelengths of light, we can't even buy these types of bulbs anymore. And you heard about the Nobel Prize being awarded to the person who discovered the blue LED, which has allowed us to create white light from LEDs. And so they're all, since the cheapest way of doing that is to start with the blue and then use various tricks to make it appear white, that means that they're all greatly enriched in the very wavelength that is most effective of suppressing melatonin and shifting our circadian rhythms. So what to do? We have, as Roz mentioned, we are re-outfitting the International Space Station with special lamps. You can't buy these in the store because they're $300,000 a piece, but in any case, not including delivery charges. But we can adjust both the intensity and the wavelengths of these lights. In fact, we were just excited yesterday. We received the Johnson Space Center Director's Innovation Award for the development of this technology that will be fully installed on the space station by next year, to help facilitate so they can get exposure to longer wavelengths of light in the evening and shorter wavelengths of light in the morning to try to keep their circadian system entrained. But there are even low-tech solutions. So in a hospital neonatal intensive care unit, simply enshrouding instead of having the child 24 hours a day exposed to light while they're in the NICU, if you enshroud them in darkness during the daytime, their weight gain is better, their oxygen saturation, they are discharged from the hospital instead of over 50 days, in 34 days, and do better on many different metrics. So what you can do is to try to focus on the amount of sleep, the timing of the sleep. It turns out consistency in the timing of sleep is as important as the duration of sleep. And then the quality, by which I mean if you have a sleep disorder like sleep apnea, I haven't had time to discuss that, then that can interfere with the ability to get the restorative value of sleep if you can't breathe and sleep at the same time. I don't have time to talk about the project that we're working on with Roz on, and this was a thesis project of Will Clerks, an undergraduate, who looked at irregular versus regular sleepers. They were sleeping the same duration, but the irregular sleepers' circadian rhythms onset of melatonin was shifted almost 3 hours later. So they were on Palo Alto time, even as they were trying to study here in Cambridge. And the bottom line was that they didn't do as well in school. These were Harvard undergraduates, and the irregular ones had a lower grade point average, a B plus versus an A minus. That's the full range of grading over there. So, that's a big deal. So anyway, so how to sleep to thrive. Try to make sleep a priority to improve your resilience. Try to establish a regular bedtime and wake time. Try to sleep in the dark. It amazes me how many people sleep with the TV blasting or lights, of their roommates or whomever on continuously. Try to make the bedroom a technology-free zone. I mean, I realize this is heresy here in the media lab, but get all these gadgets out of the bedroom. Each gadget has been shown to be associated, and TV being the worst, with about a 45-minute reduction in average sleep duration. So the more gadgets you have, I mean, texting. How many people get texts during the night when they're, come on. I know it's more than 2 people. All right, apparently this is goody two-shoes. Everybody turns off their phones. Okay, good. No Xboxes in the room. And find out how much sleep you would actually, many people say, how much sleep do I need? Well, when you're on vacation, not driving a car or anything, spend a couple of weeks, gradually reduce the amount of caffeine that you're taking, and see how much time that you will sleep without an alarm clock, without caffeine, and you'll undoubtedly find that it's more sleep than you're actually getting. And so reduce exposure to artificial light between dusk and bedtime. If you do need to use your computer, you might want to consider installing some free software that Michael Herf developed. It's called f.lux, and it shifts the wavelength of your exposure to your screen to the longer wavelengths of light after dusk in your area. For more information about sleep and sleep disorders, I recommend our website at the medical school in the Division of Sleep Medicine, understandingsleep.org. I thank you for your attention and would be happy to answer any questions. Yes?
How do you think that napping plays into it?
Napping, I think, okay. So if I were asked that question by someone who's complaining of insomnia, let's say a 40 to 50-year-old person who is having trouble, that it's not that they're not spending enough time in bed, but they can't, then most sleep disorders specialists would recommend not napping because it will reduce the sleep pressure when you go to bed at night. However, I have a very different answer for most people who don't suffer from chronic psychophysiological insomnia, but are just not getting enough sleep. And there I recommend adding naps to try to increase the duration of sleep. So great sections of the world have a culture in which the siesta is part of that culture. And humans seem to have evolved so that we can have sleep about 5 or 6 hours at night and about 2 to 3 hours during the daytime. And if you have that as a stable schedule, you can adapt quite well to it. On the other hand, if you have an irregular schedule, so the students in that study that I whipped through of that William Clerks did for his thesis, the students in the irregular group who didn't do as well and who had the most irregular schedules, although they slept the same amount as the ones on the regular schedule, their sleep was not only erratic, but they only slept 5 or 6 hours during the night, and then they, on average, did a couple of hours of compensatory catch-up sleep during the daytime. So that kind of irregular pattern is not a good idea, although they would do worse if they didn't do the compensatory sleeping during the daytime. But there it's really a sign of insufficient sleep, chronically insufficient sleep. So if you were doing it on a regular basis, that's great, and I do recommend it, because it's even worse if you're irregular and not sleeping, not taking the compensatory sleep during the day. Yes?
I want to get the questions on the mic too, so who'll start?
Yeah, hi. Yeah, what about taking melatonin as a chemical fix?
Yeah, so we've done a lot of studies of melatonin. It's a little difficult to get pharmaceutical grade melatonin, although after looking all over the world, we did find a company in Sudbury, Massachusetts called Pure Encapsulations that makes pharmaceutical grade melatonin. And we have found that if you take melatonin during the time that you're ordinarily releasing it, it actually doesn't help sleep. But if you take melatonin at a time that you're not releasing it, let's say you fly to Japan and you're not releasing melatonin, then taking melatonin then will significantly improve your sleep efficiency and make it easier for you to fall asleep. So, and in many people whose circadian rhythms are shifted later, let's say those students on the irregular schedules whose circadian system is not going to release melatonin until 3 or 4 o'clock in the morning because they're delayed. If they were to take, that's one condition in which the Agency for Healthcare Research and Quality, and its meta-analysis on this topic, found that taking melatonin in people whose circadian rhythms are delayed does significantly improve their ability to sleep. So, so in that circumstance, taking it, or if you have to go to bed earlier than you habitually do, then it would help. As we get older, some people, in very healthy older people, we don't see a decline in melatonin levels, but on average in older people, they go down for many reasons. Taking high blood pressure medication can lower melatonin levels because it requires beta adrenergic stimulation of the pineal gland. So if you take beta blockers, that can block the release of melatonin. Anyway, so in older people who are not releasing as much melatonin, Dick Wertman here at MIT pioneered the use of melatonin supplementation in older people. So.
Hi, thanks for a fascinating talk. I work with a startup here that's focused on sleep, and we've found, and in my medical practice, I found that even in high-functioning people like those in this room, we know sleep is important, but we don't make enough time for it.
Yeah.
What can we do, or what is being done to kind of convince the public that sleep should be a priority? Well,
other than this discussion here today. We're actually haven't announced this yet, but we're beginning at the Brigham and Women's Hospital what we're calling a Sleep Matters initiative, in which we're going to try to bring stakeholders together, and we've had a number of organizations express interest in participating in that to try to raise awareness about. And we have some, as you'll see when you go to our website at understandingsleep.org, the section on sleep apnea is headlined by Shaquille O'Neal, and he has a funny video that you can look at there, and she talks about sleep apnea. But as he said when we sat down with him, he said, you know, you've got a lot of forces aligned on the other side of the issue because you know, for each hour that the population stays awake, for each additional hour, they're consuming more and producing more. So there are tremendous economic forces. For example, the video gaming industry announced, to my horror, they said that, presently the kids are spending 3 billion hours a week video gaming collectively, 3 billion with a B. And they said our goal by 2020 is to get that to 20 billion hours a week. So they have and the only place that they're going to get that additional time is from sleep, and 25% of kids are video gaming after 9 p.m. on school nights, and a substantial fraction after midnight. And they video game with people in Australia and whatever. So, in fact, somebody in the gaming industry told me that the real insight that really got them a lot more eyeballs on the screen was when they made the game so that they never ended. So if you played a game that took an hour and then it ended, then you had some sense of satisfaction. But if you have a game that never ends, and these, it's not just video gaming, it's all sorts of, there was in South Korea, there was a couple who was so intensely involved, and you could call it addicted, going to internet cafe, taking care of a virtual baby, that their own actual baby starved to death in their apartment while they were doing that. So these companies have teams of psychologists trying to get the people engaged so that they can never let go. And those are the kinds of forces. And selling caffeine, caffeine has become energy drinks are now something like a $6 to $8 billion a year industry. In fact, I was giving a talk like this, and I showed the slides showing that there are 10 times as many people sleeping less than 6 hours than there were 50 years ago. And this was to an NBA team, and one of the star players, I was only 20 seconds into my talk trying to convince them that they needed more sleep. One of the star players said, "That's because back then there was no shit to do." And he said, and he held up a bottle of 5-hour energy drink, and he said, "This is my sleep. I don't have time to sleep." And then one of the other players said, "Well, maybe that's why you're so erratic on the court." And I was like, whoa. A little different reaction than here.
All right, I hate to be the one to bring this to an end, but it's 12 hours before the middle of the night now, so we need to go to the third floor. We're going to move our conversation, more Q&A, and lunch there.
Great.
So let's thank Chuck. And
well, thank you, Roz. Appreciate it. Thank you. Thank you very much. Thank you.